So shut up.
You better watch it because they can't fire me anymore.
Technically, they still can. His last day is
All right, so let's get going. Yesterday we talked about resistors, right? And so there are two circuit components you know how to work with for AP Physics. The first one is resistors, and we kind of talked about covering all of those. What we're going to talk about today is capacitors. You have to do basically the same stuff. So like what they're going to want you to do with either one of those things is they're going to give you a circuit with all the stuff in there, and they'll be like, hey, find the current, find the resistance equivalent of the whole circuit, all those kinds of things. And the mathematical analysis of that kind of sucks, and it's one of those things that you just kind of learn by doing, but at least you have the core principles for it now. Today, we're going to talk about all the same stuff for capacitors. So just like yesterday, we talked about what is a resistor, and then how do they behave in circuits. Today, we're going to talk about what is a capacitor, and then how do they behave in circuits. Does that make sense? We're relying on the same two principles we learned yesterday, though, when we get to that circuits thing. So I'm just going to remind you of those briefly. So the two things that we learned about are that series circuits, everything is in a series, right? One component leads directly into the next one, and that means that the current is the same throughout the entire circuit, but the voltage needs to add up as it goes around, right? Does that make sense? Basically, one of those is using the idea of conservation of charge, that I have a set amount of charge, so any charge that moves through this side has got to move through that side, and that leads to charge per second, which is current, right? The other is conservation of energy, right? If the battery provides this much energy, I've got to use up all that energy by the time I get back to the end, right? That's basically the logic that we use to be able to say that the voltage drops need to add up. Does that make any sense? Okay,
Yes.
you're allowed to respond to my questions.
Okay.
Just don't. You can respond to questions, you can ask questions, just don't be like talking about whatever that stupid movie is that y'all were talking about. It's not really, whatever. But I love that y'all know the word art house now. Okay, so let's talk about capacitors. And what capacitors come down to is what we're trying to do is we're trying to store charge. That's what a capacitor does. This is not the same as a battery. All right, so we've kind of talked a little bit about a battery provides a voltage, which is essentially an energy difference that makes charges flow and do all sorts of things, right? Capacitors are not the same thing because they're not storing an energy difference. What they're storing instead is literal charge, like they store like actual electrons. Does that make sense? That's what a capacitor does. So it does a different thing. The reason why we want capacitors is, well, there's a lot of reasons, but one of them is it's useful to store up charge and then be able to release that charge. For example, like the old school flashes on cameras, they use capacitors to provide a very quick jolt of energy to like make a bulb flash instead of just come on. Does that make any difference or make any sense? The other thing that capacitors are useful for, and most people don't know this, is that there's a lot of data storage that uses capacitors. For example, those little thumb drives use flash storage, and the way that those work is basically they have lots of little capacitors that store charge, and then based on what arrangement those capacitors are charged or uncharged, that's how you store data in. So like if you know anything about computers, you may know that they use binary language to store and communicate information. Well, if a capacitor is charged, we call that a 1. If it's uncharged, we call that a 0. And so now if I have a ton of capacitors, I could charge them in the arrangement that would match the data, and now I have a readable file. Does that make any sense? So capacitors are really useful for lots of things. We will put them in circuits that basically do nothing, only so then we can study what they're doing, or study how they behave. Does that make any sense? So just so you know, you'll never find a circuit like what we're doing with capacitors today, at least not a very useful one. But if you can learn the principles of how they behave, then you can do more useful things with them. So like we'll also talk about RC circuits, which have a resistor and capacitor. Those actually are useful, and so we'll talk about those after we've covered all these things. Does that make any sense? I say that. I actually made the decision today not to cover RC circuits with y'all. like right now. The reason for that is because I think without having had enough practice with resistors and capacitors, it's just not going to do you any good. So instead, because like the way that I typically do that, you would have to understand those other two things. So instead, you'll just be on your own with those, but they're not that complicated. All right, so let's get into what we're actually doing today. So we don't need all that. So here's what a capacitor could look like. So basically, most capacitors, what they do is they take a circuit, and I take two metal conducting plates and I put them near each other, right? The reason I do that is because if they're really close together, we've talked about kind of this phenomenon of like polarization and attraction and all this kind of stuff. Well, if I take, say, a negatively charged thing and I bring it near a neutral thing, it's going to pull positive charge, right? So a similar phenomenon will happen where if I put a battery connected to two plates, well, one side of that battery is going to be positively charged, one will be negatively charged, and what I should see is that it will push or pull charge as appropriate, and I'll end up getting the two plates of the capacitor to store charge. So what I mean is this: if I take a battery and I put it across a capacitor like so, this is positive and that's negative, right? So this positive terminal of the battery is going to attract electrons to it, right? Which will end up leaving this side negatively charged. This negative side will push electrons, wait, I said it the wrong way, positively charged. This negative terminal will push electrons away from it, which will leave that negatively charged. And now, as long as this battery is hooked up, that essentially is holding and storing charge in the circuit. Does that make any sense? Because of these energy differences, I end up storing charge, which is great. That's a really useful thing to do. So it turns out that the capacitance of a capacitor is just a function of how the capacitor is created. So capacitance is the amount of charge that can be stored on a capacitor per unit of potential. So a capacitance is a measurement that fits the actual capacitor. So a capacitor could have a capacitance of, however many coulombs per volt. And then the amount of charge stored on the capacitor will change depending on how strong the voltage is that you put across it. So the stronger the voltage, the more charge it'll hold. Are you guys okay over there?
Mm-hmm. We're not talking.
Which actually applies today.
Yeah, well, I just I look over and y'all are all being goofy weirdos, even though you're not talking. So this is just a little bit concerning. I mean, it's fine. I'm not upset with you. I'm just noticing odd behavior. All right. Okay, so the way that we calculate the capacitance is it's only based on the physical dimensions of the object, as well as, I should say, this thing in the middle, which we call a dielectric. I can change out that dielectric with different types of material, and depending on what material is in there, it will alter the capacitance of that material. But in general, here's the equation. The capacitance is equal to the permittivity of that dielectric. We've seen that term before, right? It's like how hard it is to set up an electric field within that material. It's equal to the permittivity multiplied by A over D, where A is the area of the plates and D is how far apart they are. So what you may see here is that the larger the area of the plates, the more charge can be stored. That kind of makes sense, right? It's like there's more space for charges to spread out. That's a thing. And then the distance apart. The reason that matters is because the closer those two things can get together, then the stronger the electric field is going to be between those two things, and therefore the more it's going to pull charges to it. So that's why that one's on the bottom. The closer the plates are together, the more capacitance it's going to have. Does that make any sense?
Mm-hmm.
Okay. So that's how you build a capacitor. Notice here that the dielectric can change. So you'll see this equation written in terms of epsilon instead of epsilon naught. So different dielectrics have different constants K And so if you're going to swap those out, you just make it K times epsilon naught. It's not that big of a deal. So epsilon naught represents the permittivity of vacuum, and you may have to multiply that by some permittivity constant. It's not that big of a deal. All right, here's a table of dielectric constants, so you can see different things you may want to put in there to increase the capacitance. So notice air has a dielectric constant of 1, so it's essentially the same as vacuum. But then like you've got all sorts of other stuff that people use. So for example, is it on here somewhere? I thought it was. Don't see it. Anyways, this strontium titanate, that's like really high quality. They use that in expensive capacitors to make them have lots of storage. Water is a pretty good one. But you've got different things you put in the middle. That's really all you need to see there. I don't think we really have time for this. So let's just move on. All right. That one I think was just a bonus. Like, I find this interesting, so I'm going to talk about it anyways. So when I put a capacitor in a circuit, I can use this capacitance equation to determine how it's going to behave, right? So if I use that other equation to determine its capacitance, then I could figure out if I put this voltage across it, how much charge that capacitor is going to store. So you can think of this, C equals Q over V, as an analog for Ohm's law, right? So when we looked at the last thing with the resistors, we used Ohm's law, which was all about how the resistance is going to affect current. We use that to analyze the circuit. Similarly here, I use this definition of capacitance to analyze the circuit. It's a useful mathematical formula for that. Make any sense? It's also useful for me to tell you, like, the capacitance is, whatever number, then when I put different voltages across it, I'll see the charge stored go up, right? That's an important thing from this. Why are you not clicking? Wait, is that the end of this slideshow? It might be, actually. It is, in fact, the end of this slideshow. Okay, so that's the basics of capacitors. Do you guys have any questions before we talk about capacitor circuits?
No.
So if this was like a normal class, I would have taught you all that, and I'm going to give you time to like mess with the simulation to see how changing the different dimensions and stuff changes the capacitance of the thing. Just give you a little bit of like semi-hands-on learning. We don't have time for that. So, we ready for capacitor circuits?
Mm-hmm.
All right, so basically we're going to look at the same two arrangements as we looked at the other day with resistors. We're going to look at what happens when they're in series and what happens when they're in parallel. That's not important. All right, so quick reminder, capacitors store charge. The capacitance depends on the physical attributes. When we do all of this stuff, we're going to basically assume that you already know the capacitance of the capacitors, and you're not necessarily applying this equation to figure out what the capacitance is. Though you'll see some circuit puzzle questions that'll be like, here's what we know about the circuit, find the capacitance of capacitor 7. You might see that, whatever. This is our important equation. So remember, this is analogous to Ohm's law. So we did all this stuff the other day with Ohm's law. This is going to serve the same purpose. So basically, it's like our bread and butter equation when we're solving capacitor circuits. So it is that C is equal to Q over V. We will rely on that here in just a moment. So if we look at things in series, important to make sure we have the right idea here. So I've got a battery, and let's say that I have two capacitors in series. So the way we represent capacitors in a circuit are just two equal length lines. So notice a battery is two not equal length lines. A capacitor is two equal length lines. When we're drawing our diagrams, that's what they look like. So when we look at capacitors in series, I need to apply that concept of the conservation of charge. And here's what I want you to see happens if I do that. If I assume that one terminal is positive and one is negative, then I would know that this terminal being positive, sound good? Mm-hmm. Means that that's going to make this side of the capacitor positive, this side negative, right? Now watch the behavior here. Now I'm going to have this negative end pushing electrons over here, which is going to make this a positive, this a positive. And if this is a positive, then that's going to be negative. And so what I end up with is that all of my capacitors will end up having the same arrangement, plus, minus, plus, minus, plus, minus, plus, minus. Does that make any sense? Okay. Now, if that's what happens, I run into an interesting situation at this guy in the middle, right? Before I put the battery in, I've got zero charge here, right? Total in this little segment. Are we comfortable with that idea?
Yes.
So then all that happened here was this middle segment polarized. Now what that means for us is that I'm going to have the same amount of charge over here as over here. And if I apply conservation of charge, then what that ends up telling us is that in series, all of my capacitors are going to have the same charge. This is similar to our idea about current, right? Except that capacitors don't have current flowing through them. Instead, they collect charge on them. The important takeaway is that in series circuits, I'm going to have all of my capacitors having the same amount of charge on them. Does that make sense? Okay. The other thing is also true, that I'm going to have the same voltage drops. So, equal charge on all of them. Conservation of energy would then tell me that I have to have the equal voltage, not equal voltage, that the voltage drops all the way around have to add to the source, right? If I combine that logic, I'll show you the derivation here, then I could use a very similar mathematical statement to what I used the other day, where I say that, well, the voltage of the battery has got to be equal to the voltage across the first capacitor plus the voltage across the second plus yada 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 all the way to the nth capacitor, right? Now the charge stored on each of these has to be the same, and so I could use this to make a substitution where what I'm going to find is that the voltage is going to be equal to the charge divided by the capacitance. Okay with that? I just rearranged this equation. So if I'm looking for this like equivalent capacitance, I could substitute in here. And now remember, this is the same for everything. Divided by the equivalent capacitance is going to be equal to the charge on this divided by its capacitance plus the charge on this divided by its capacitance plus so on and so forth. These are all the same Q, so just like the other day, I could divide both sides by Q, and I end up with this equation here. Now what's interesting about this is that this actually looks quite a bit like what we saw for parallel circuits with resistors. So what you're going to find out here in a minute is that basically the rules for how I analyze these circuits, they're reversed. And the reason why they're reversed is because you may have noticed that this relationship is an indirect proportion with voltage, whereas with Ohm's law, it was a direct proportion with voltage. And so you just end up with those two relationships flipping around because those relationships are opposite. So, spoiler alert, I'm going to get this statement for series, which is very similar to our statement for parallel for resistors. When I do the next one for parallel, you're going to end up with, the same statement we got for series for resistors. So you end up with the same relationships, but they're reversed. So when you go to analyze things, you don't have to memorize a ton of this stuff. All right, capacitors in parallel. If we look at capacitors that are in a parallel arrangement, what you'll see is that now, if I apply the conservation of charge, well, let me just draw it. Hold on. So here's our battery. I'm going to have two parallel capacitors. So now if I look at applying the same principles, what I'm going to see is that both of these are hooked up directly to the battery, and therefore they have to have the same voltage, right? You're talking about that. What I'm also going to see is that if you think about it this way, the charge is now going to be split between these two, right? So what I'm going to see is that the total charge stored is going to be the sum of the charge on each of those branches. Does that make any sense? Whereas before, they all had the same charge because they were in series. Now what I'm going to see is that they don't have to all have the same charge, but the charge on each has to add up to the total charge that's stored. You know what I'm saying? So I end up with kind of a different statement. If I use that the charge has to add up, then I'm going to get the total charge is going to be equal to the charge on 1 plus the charge on 2 plus yada yada yada, the charge on the nth one. And then I can use this statement, rearrange once again to say Q equals CV. And I could substitute to say that the total charge then must be equal to the equivalent capacitance multiplied by the battery voltage. And when I look at all of these, each of these are equal to its capacitance multiplied by the battery voltage, because they're all hooked up to the battery directly. And then once again, it's all the same voltage. I can divide it all off, and I see that the equivalent capacitance is just equal to the simple algebraic sum of the capacitors. So again, notice same two relationships that I had with resistors, but they're flip-flopped, right? So with resistors, it's a simple algebraic sum in series. It's that weird inverse sum thing in parallel. With capacitors, it's flipped. The weird inverse sum is series. The simple sum is parallel. Does that make any sense? Mm-hmm. And that's really all there is to it. There's a couple of equations. You puzzle through different types of things. It's very much the same as what we saw yesterday. Does that make any sense? Mm-hmm. Okay. That's really all there is to it. And then you should go and work on them. You'll see that you have a similar thing with these circuits where what you're going to have to do is look at a complicated circuit and you're going to have to figure out, well, is this circuit primarily parallel or is it primarily series? And you got to start breaking it down from there, just like before. It would probably be a good idea for me to show you one or two of those. Let me grab a worksheet to show you.
Newspaper. No, but I have an idea.
All right, so here's one. So, just like yesterday, did they say breaking news?
Yes. You don't understand, Mr. Wilson.
You're right, I don't. All right, so just like yesterday, I would have to take a look at this circuit and try and figure out what kind of circuit it is and then start breaking it into elements, right? So the logic that we used yesterday was try to determine first what kind of circuit it is overall. So if you just use your finger and trace along, you're trying to look for, do I hit a branch on each side first, or do I hit an element on either side first? So if I trace along this way, look, there's an element. So this is this overall series circuit. But I'm going to hit a branching here. So I would call this a series circuit with a parallel element to it. Does that make sense?
Yeah.
So when you go to start writing out your mathematical equations, you're going to write them out that way. So when you find the equivalent capacitance, in this one, I would start with that 1 over equivalent capacitance is equal to 1 over the capacitance of this guy, which is 10 farads. Plus, I then have to do, 1 over the equivalent capacitance of this parallel guy, right? Which that's just a simple algebraic sum. So you're going to start doing the same thing as before, right? We're going to make those big statement, and I'm going to just label this CP, and then I will go in and I will substitute in the way that I found that capacitance. And when you have really complex things, let's see if I got anything that's really complex here, maybe like this one, then you'll start getting more and more. So notice this guy, if I trace this way, I hit a branch first, let's try the other side. I hit a branch first, and so this would overall be a parallel circuit. This parallel circuit would have 3 branches, one of which is a series element. So again, when you go to do it, you would say the equivalent capacitance is going to be 10 plus 15 plus this guy. Does that make any sense? Okay, that's why we only got about 2 or 3 minutes left on the video, but I'm almost done, so I'm just going to let it run out. So again, when you're doing this, try to identify what is it overall, and then start substituting, right? So if I make a mathematical statement, I can go in and just keep substituting those things. Let's see if we got anything else that's really complicated here. No, that was it. Actually, there's only 2 on that one. These take a long time to solve, so get excited about that. So you'll see lots of questions like that that'll say, here's the circuit, find the charge on every capacitor and find the equivalent capacitance, right? That's pretty standard. Just like we saw the questions yesterday or Friday, whatever it was. That was like find the equivalent resistance and then find the current through every resistor. You can also apply some logic here like this of saying, you know, if I look at this circuit, the voltage across each of these must be the same because they're in parallel with each other, right? So there's an important thing to help you solve that puzzle. If I look at this guy, I would know that the charge on each of these is the same because they're in series. So you can kind of think through those same lines of logic. That's why I've tried to emphasize those in each of these lessons, is to start with how does this circuit behave first? Because that's what's going to help you solve the stuff. The mathematical statements are going to help you find numbers, but understanding those principles is what helps you know when to apply what, right? So remember, really important. I'm going to summarize the principles really quick, and then I'm going to be done with you guys. When we look at resistor circuits, what we see is that in series, they all have the same current and the voltage adds. In parallel, we see they all have the same voltage and the current adds. When we look at capacitors, you see similar behavior, right? When they're all in series, they all have the same charge and the voltage adds. When they are in parallel, they'll all have the same voltage and the charge will add. Those principles need to be things that you remember because that's really what will help you puzzle these kinds of things out, is knowing those pieces of information. Other than that, you're just going to have to get experience solving these out. When I see you tomorrow, we'll talk about Kirchhoff's laws, or sometimes called Kirchhoff's rules. Those will actually give you a way to just like write out equations and solve a system of equations so you don't have to think about it. But I think it takes quite a bit of time to do that well. And so I think if you can, for simple circuits like this, working it out this way is probably easier. So that's it. Do you guys have any questions?
Can you explain how to, I mean, like, I feel like I know, but the parallel versus series capacitors, like, track with the hand and traveling.
Like how to tell which one it is? So the easiest way I know how to do it is basically, if there's anything in series with the battery, it's a series circuit. If I hit branches, then it's parallel. Okay. So I just literally take your finger and trace it. So notice here, if I trace this along, I hit an element before I hit a branch, so this is a series circuit. Okay. If I didn't hit an element, then I would actually have to test the other side too. Okay. Because like if this was over here, like the battery doesn't know which way you're going, right? So if, stop it. I don't want to touch you.
Because that would be a series connected to a parallel, right? Because the other one branches out, right?
Yes.
Okay.
Yeah, so I would say this is a series circuit where what I would do is in my mind, these things in parallel, I think of as one component. Okay. So in my mind, this has 2 capacitors in series. Yes. One of which is made up of these 2 in parallel. Okay. Does that make any sense?
Yes.
So, and I think that's the best way to try and think about these circuits when you're doing them, is what is the overall structure? I'm going to treat it like that. And then this thing, for all intents and purposes, could be considered one object. Right. And then I don't think about it as 2 until I have to. Right. What I was trying to say earlier was if this was down here, the current's just flowing the way it's going to flow. So that would